Hello everyone. Today we will again solve another problem on the voltage divider circuit. So here you see the question. Determine the bias point, that is ICQ and VCQ, for voltage divider configuration which is shown in the circuit using both exact and approximate technique, and you have to compare the result. So this is the voltage divider circuit, and the circuit is common emitter configuration. So R1 and R2 are 82 kilo ohm and 22 kilo ohm. Supply voltage is 18 volt. So RC is 5.6 kilo ohm. RE is 1.2 kilo ohm, and beta is 50. So for this we have to do it for both the exact and approximate method. So first we will start with the exact analysis. So in the exact analysis, what we do, we calculate the value of, we will convert this into the equivalent Thevenin's network at the input side by having an Thevenin's equivalent voltage and Thevenin's equivalent network for the input circuit like this, right? So this is RTH and this is RE and this is ETH. So ETH is nothing but the voltage across R2, which is voltage across the resistance 22 kilo ohm. So to find out ETH, so which is voltage across R2 or voltage across base to reference, which is VB, right? So what I told, the voltage across 22 kilo ohm, which is R2, or voltage from base to reference, or ETH, right? So is represented by voltage across 22 ohm. So 22 kilo ohm into current is VCC by R1 plus R2. So VCC by R1 plus R2, which is 82k plus 22k, right? So by solving this we will get ETH or VB as 3.81 volts, and correspondingly RTH is nothing but R1 parallel with R2, that is 82k parallel with 22k. You will get RTH as 17.35 kilo ohm, right? So this is the RTH and ETH or VB. So in the exact analysis, what we do, we calculate the value of IB. So IB is calculated, IB means the IB which is flowing through the base of the transistor. So IB is ETH or VB minus VBE divided by RTH plus, so the current flowing through this with respect to IB is 1 plus beta times of RE, right? So on solving this, we will get 3.81 volts minus 0.7 divided by RTH is 17.35k plus 51 times of RE, which is 1.2 kilo. So on solving this, you will get IB as around 39.6 microamps, right? And once you get IB, you can get IC, which is beta times of IB, which you get it as 1.98 milliamps. So this is ICQ. So now to calculate VCEQ, you can apply KVL across the output loop, which is given by VCC minus IC into RC plus RE. So because IC and IE are one and the same, so IC into RC plus RE. So this is VCE, right? So VCC is 18 minus 1.9 milli into RC 5.6 kilo plus 1.2 kilo. So on solving this, VCEQ you will get up around 4.54 volt. 4.54 0.54 volts, right? So this is using exact analysis, right? So now using approximate method, we check for the condition which is beta Re should be greater than 10 times of greater than or equal to 10 times of R2, right? So beta is 50, Re is 1.2k, should be greater than or equal to 10 times of R2, which is 22k, right? So now what happens, this is 12 is a 60k and this is 220k. So this is not satisfied here, it is not even equal to, right? So in this case what happens, we don't calculate the value of IB, we don't do it using IB. So we will calculate ETH or VB, which is 3.81 volt, which we have calculated Thevenin's voltage. So using this we will calculate VE, which is VB minus VBE. So this is 3.81 minus 0.7, you will get 3.11 volt. So this is VE. So once you get VE, you can calculate IE, which is VE by RE, so which is 2.59 milliamps, right? VE is 3.1 volt and RE is 1.2 kilo, right? You will get 2.59 amps. So similarly for VCEQ is equal to VCC minus IC into RC plus RE, whereas here IC is 2.59 milliamps, so it happens to be 18 minus 2.59 milli into 5.6k plus 1.2k. So VCEQ you get around 3.88 volts, right? So here we get both ICQ, which is IE is nothing but your ICQ itself, and VCEQ using approximate method is 2.59 and 3.88 volts, whereas in the exact analysis you will get IC as 1.98 milliamps and VCEQ as 4.54 volts, right? So I will just summarize it in the exact analysis and approximate analysis, right? So in the exact analysis we get ICQ and VCEQ. ICQ is 1.98 milli and VCEQ is 4.54 volt, whereas using approximate method your IC is 2.59 milliamps and VCE is 3.88 volts, right? So this is the summary of the solution, which you calculate the bias point using both exact and approximate method. So here you see the value of ICQ is increased by almost 30% in the approximate method compared to exact analysis, right? So ICQ, the current is increased by 30% compared to exact analysis, whereas VCEQ it is 3.8, it is decreased, it is almost decreased by around 10%, right? So this is the difference what you find between exact and approximate analysis, and among this which one is valid? It is obviously the exact method, not the approximate method, because in the approximate method this condition is not satisfied. So since this condition is not satisfied, both will not be approximately equal also. So you see here the current is approximate method, in the approximate method it is 30% more and the voltage is 10% less compared to the exact analysis, right? So this is the solution, and in the next class we will discuss about